this lecture, we're going to have a short introduction and also some basic concepts about the turbomachinery flows. So this is our outline for this course, and we're going to start with the theory and analysis of turbomachinery flows, and then look at the axial flow compressor and fans, then the centrifugal compressors, and following by that, it's the axial flow turbines and radial and mixed flow turbines. Then in the first part, we're going to finish with the unsteadiness, turbulence, and 2 and 3-dimensional loss mechanisms inside turbo machines. And the second part of this course will be the data acquisition techniques in unsteady turbo machinery flows and non-optical measurement techniques, and also the optical measurement techniques. The non-optical measurement techniques that we're going to cover is the hot fire or hot film measurements and multi-hole P2 and high frequency response pressure probes. And for the optical measurement techniques, we're going to see the LDV, which is the laser Doppler velocimetry, and laser two focus velocimetry, L2F, and then the particle image velocimetry, PIV, and Doppler global velocimetry, DGV, and pressure sensitive panes, which is PSP. And besides this, if we can finish these materials soon, we're going to have a third part which will cover some concepts of designing the turbo machineries in ANSYS. In ANSYS, so you would be able to at least analyze one or two cases of turbo machineries like fans or compressors or whatever turbines. You can model them and you can analyze them inside ANSYS. So what is a turbo machine? Turbo means rotating, and turbo machines are devices in which you have a transfer of energy between a fluid, which is continuously flowing, and let's say rotating element. And this transfer of energy is actually happened by the dynamic action of one or more blade rows. This, of course, results in a change of pressure and momentum of the fluid. So the pressure and momentum is changing. So whether you are taking energy from the fluid or you are giving energy to the fluid. And a machine that can do this is called a turbo machine. Based on this, we can classify turbo machines with different viewpoints. First of all, you can have an external flow or an internal flow turbo machine. And some examples of the internal flow turbo machines are pumps, compressors and turbines of a turbojet engine, and etc. And the external turbo machines are like the cooling fans, helicopter rotor, and aircraft propeller. So I guess you're familiar with some of these machines. In a different viewpoint, you can classify the turbo machines into three, let's say, categories like axial flow and radial flow, and in between there is a mixed flow turbo machine. So based on the flow direction, you have this flow inside the turbo machine that is parallel to the principal axis or shaft. So this blue one in the middle is the shaft of your turbo machine. So this is a kind of axial compressor in here. You can see it. So flow comes inside and leaves outside the turbo machine parallel to the shaft. So we call it as an axial flow. And then in the radial flow ones, as you can see, flow enters the machine along this shaft. So this is the shaft. So flow enters along the shaft or principal axis, and then you can see that it turns like 90 degrees and leaves the machine in a radial direction. So you have this radius in here and it leaves in a radial direction. So there is a 90-degree difference between entrance and exit. And in between of these axial flow and radial flow, you can have this mixed flow machines that in the mixed flow machines, flow usually enters along the axis or along this shaft, and then it is leaving the machine at a certain angle with respect to the axis of rotation. So it doesn't have to be exactly 90 degrees. When it is 90 degrees, we have a radial flow machine. When it is some other degrees rather than 90 degrees, it is a mixed flow machine. Uh, in the viewpoint of the fluid density change, you're familiar with the density. So if a machine can change the density of the fluid, we call it a compressible machine. And if the fluid density is not changing, we call it incompressible machines. As an example for the incompressible ones, you have hydraulic machines like pumps and fans. And for the compressible ones, which we call it thermal machines, we can give examples of compressors and gas turbine. So we said that we have this energy inside the fluid, or we can give some energy to the fluid, and this energy which is flowing between the fluid and the rotating element is going is happening, let's say, from the viewpoint of the energy transfer direction. So whether it's coming from the fluid or whether it's coming from the rotating machine to the fluid, we can have power developing machines or producing machines, and also power absorbing turbo machines. So power developing, as you can see, this is the example. The wind turbine. Wind turbine is developing or producing electricity for us. And the example for the power absorbing machines is very clear to you. This is a fan, so we give electricity to this and it rotates, so it absorbs the power. It gets the electricity and gives the energy to the flow to the fluid, and completely uh, reverse thing happening in the wind turbines. So it gets the fluid energy, it gets the air energy, and then it converts it to the electricity. So in the power developing or producing machines, these machines always expand fluids from high to low pressure, and they recover energy, like the turbo expanders in petrochemical plants, or extracting energy from a stream like the wind or hydraulic or steam turbines. And these are driving electrical generators, pumps, and compressors. And also in jet propulsion, you see these in aircraft jet engines. For the power absorbing machines, they are impelling, pumping, and rising liquids like pumps, and also blowing and moving gases like in fans, or compressing gases. And as an example, in jet propulsion, you can have turbojet and turbofan and turboprop engines that they have some turbo machines that are absorbing power. So these power developing or generating turbo machines, you saw that if the flowing fluid transfers energy for the rotation of the impeller fixed on the shaft, it's known as a power generating turbo machine. And as an example, we said the steam turbine, gas turbine, wind turbine, hydraulic turbine. So turbines are something that generating or developing power for us. On the other hand, we have power absorbing turbo machines. We said that if the machine transfers energy in the form of angular momentum fed to the fluid from the rotating impeller mounted on the shaft, it's known as a power absorbing turbo machine. So all the pumps, compressors, and fans, also blowers, are in the group of power absorbing turbo machines. In this slide, you can see examples of radial in the left, and also axial uh, axial turbo machines. So in the right, in the left part, the centrifugal or radial machines. This is an example. See, this is a suction side of the machine. So this is rotating, and by rotation, it sucks the fluid inside. So water or whatever liquid goes inside. That's why we call it pump, um, a hydraulic pump. And then it shoots the liquid or water in 90 degrees angle to the entrance. So that's why we call it radial. And this hydraulic pump that we have in here is working with higher heads and low flow rates. On the other hand, of the radial machines or radial pumps that we are talking right now about, we have an axial or propeller pump. So as you can see, this sucks in the water or any liquid, and then it gives it out. By the way, the entrance and exit of the pump are both parallel to the shaft of the pump. Okay, so this is the drive. There is a shaft in between. This is the red shaft in here. When it enters and when it leaves this propeller, it is in line with the shaft. So don't look at it and say it's 90 degrees. So it's just a tube. And these axial propellers are very good working in the lower heads. So these, as you can see, these are centrifugal ones work in higher heads, but these are working in lower heads, but with a very higher flow rates. Now let's look at the fans in here. We just talked about the pumps. Now look at the fans. So the fans are like pumps. So the basic thing that is happening inside the fans is like the pumps. The only difference is that when you're talking about fans, you're talking about gases. But when you're talking about pumps, you're talking about liquids and water, so, water-like liquids. The pressure change inside the fan is very small, but it's small enough to consider constant density. So a fan usually doesn't change the density, so it's incompressible turbo machine. Uh, and fan construction is much lighter than that of pumps because, as I said, fan is dealing with gases, and uh, gases densities are very smaller than the liquid densities. So order of magnitude lower than liquid densities means that you can make fans very lighter than the pumps. And you can see both axial type and radial or centrifugal type of fans in the figures. Okay, uh, we saw what is pump, we saw what is fan, and now let's look at the compressor. So compressor, the name suggests that it compresses, and the compressor is dealing with the gas, so it compresses the air. It means that the fluid inside is happening to change its density, and these also work like pumps, but the pressure rise in the compressor is very high. And as we said, the gas density changes are considerable. And as a as an example, you can see one um, axial configuration and one radial or centrifugal configuration in here. So in this radial configuration, flow comes from left to right. Okay, this is the shaft, and then when it is rotating, it sucks in the gas, and then it shoots it in the radial direction out. This is a centrifugal compressor, and in the figure below, you can see an axial compressor. So this axial compressor, as you can see, has too many stages. What is a stage? A stage is uh, a set of two rows of blades. So one row is rotating, like this row, and another row which is in between, and it's not shown in here, it is not rotating. These two sets of rows, we call it a stage. So what are these? We will look at them later. These axial configurations require several steps or stages to achieve the desired compression effect. Why they need, let's say, several steps, we will look at it later. Because as you can see, this is a multi-stage, we call it multi-stage compressor, but in here you can see that it only has one stage. So this is only rotating. These blades only rotating, and then it compresses the air. So uh, we said that in an axial, let's say, turbo machine, or specifically talking about compressors in here, we have some blade rows that are rotating. We're calling them rotor blades, and some rows that are not rotating, which we call them stators. Diffusers, this name is a kind of a stator inside a radial or centrifugal machine. So for a radial or centrifugal machine, if we are uh, actually aiming the stators, we call them diffusers. But when we are talking stators inside the axial machine, we are using stators. So what is the usage of these stators or diffusers? Actually, they are there to just convert your kinetic energy into some pressure. So we have a compressor. Compressor is to, let's say, give rise in the pressure of the air. So what actually does this pressure rise? The diffuser or stator inside the compressor. So what does the rotor do? Actually, rotor gets the fluid, gets the gas, gives some kinetic energy to the gas, and then passes this gas to the set of the stators or diffusers, and then these stators and diffusers are there to convert this kinetic energy to pressure. Do we have any questions so far? I'm sorry, Usman, because when I'm presenting, I cannot see this public chat in here. So you have asked that what does head mean there? Did you take fluid mechanics before? So you had head rise in fluid mechanics. And if you remember, head rise was something that was dealing with the uh, pumps and stuff. Do you remember the head rise? Oh, okay. So if you want, you can come to me after the class and I will explain it to you. So in liquid handling machines, there is a specification or characteristics of pump that you call it as head rise. How much this pump can rise the head, and head, the unit of head is in meters. It means that if you put this pump inside this building, how much meters can this pump shoot the water to the higher, let's say, stairs of this building. So this is called head rise of the pump. Okay. And as a note in here, um, when you're checking the radial or centrifugal compressors, you cannot find a centrifugal or radial compressors that has more than three stages. The stage I meant one rotor and one stator sets of blades. Don't worry, we will look at these later, but right now, just to get familiar with the idea of this course, we are giving this much of information to you, so uh, you can see what are the subjects included in this course. And we said that the axial compressors or turbines are always multi-stage, and as I said, we will check why this is happening in axial machines. So these those are the keywords that we were looking. First of all, we have a fluid in a turbo machine, and we said that this fluid is interacting energy with the machine, and this machine has rotating parts. That's why we call it a turbo machine. So what is this fluid? We said that this fluid could be air, could be water, and could be other liquids, and could be other gases. Also, for an example, you have cement, cimento, and you have steam, buhar, and blood. So all of these could be also inside a turbo machine and interacting with the turbo machine. We said that we have a stage. So a stage definition is a stage is composed of a rotor and a stator. So you have one rotor, you have one stator, like in here. See, these are the rotors. What is this? Again, you're seeing one of these, let's say, blade rows from the side view. So just look at these two ones in here from the side view. You're seeing these, you're seeing one rotor set and you're seeing another stator set. So we call these two together as one stage. Rotor, it's a dynamic element. Why is it dynamic? Because it is rotating. And a stator is a static element. It's not rotating. It's only there. And what is the actually role of this stator? We said the stator gets the high kinetic energy fluid from rotor and turns it into pressure. So it gets energy and turns it into pressure. When we are talking about a multi-stage um, turbo machine, we mean that a number of stages to achieve certain enthalpy rise or drop is uh, some number. So you have two, three, four, five, six number of stages, like what you're seeing in this figure or in this figure. So mm, right now I'm talking about the figure in the bottom. As you can see, these are mentioned by some colors and also some letters. The first is IGV. What do we mean by IGV? It is inlet guide vane. Inlet guide vane. So it's there only to guide your flow into a specific angle. After this inlet guide vane, as you can see, you have a rotor and then a stator, and then again rotor, stator. And as you can see in above, the first stage is the IGV and rotor. The second stage, again, it's a stator. So IGV, it's like a stator because it's not rotating. And then a stator, rotor, stator, rotor. So each stator and rotor makes one stage for you. And then at the back, you have EGV, which is exit guide vane. And again, this EGV is there to just direct the flow into a desired angle. Uh, we said that we are using the compressor or turbine to either increase the pressure or decrease the pressure. This pressure also shows itself into the enthalpy. Do you remember what was the enthalpy in your thermodynamics? The enthalpy was defined as your Cp times temperature. And if you remember, you had a total enthalpy H0, which is your enthalpy plus the uh, kinetic energy. So 1 over 2 U squared is actually your kinetic energy per unit mass. You remember your kinetic energy was 1 over 2. Can I write in here? I'm not very familiar with. I guess I can write. You had kinetic energy was writing with a mouse is very hard, guys. 1 over 2 m v squared. So kinetic energy per unit mass is like 1 over 2 v squared. This is 1 over 2 v squared. So this is your total enthalpy. So the action of the compressor is to really rise the enthalpy, and the action of the turbine is to drop the enthalpy. And mm, I'm very strict about the units. So if you're given a problem, just don't forget to put the units of what you're calculating. This enthalpy unit, if you remember, was joules per kilogram or meter square per second square. So do we have any questions so far? Inner energy. Mujahid, we were talking about the inner energy. What is inner energy? Internal energy or inner energy? Internal energy. Yes, actually, this enthalpy was something related to internal energy as well. You're right. That's why we have temperature in here, because whatever you have that has higher temperature, you can say that it has higher internal energy as well. Okay, so far you saw these hydraulic pumps and then fans and then compressors. Now let's go to gas and steam turbines. So we said that turbines are there to just drop the enthalpy or just get some pressure from the fluid. Uh, on one hand, we have these radial machines and radial inflow machines, radial inflow turbines. So it means that the flow comes radially inside the turbine and then leaves axially like this. On the other hand, you have radial outflow turbines. So as you can see, you have for example, a steam or something that is coming in line with your shaft, and then you can see that it is leaving radially. So there are two, these are the two type of gas and steam turbines. So the main role is to expand a high pressure stream to lower pressure while extracting power from the fluid to move a shaft. Turbine is there to do like this. And we said we just saw that the radial inflow designs are most common, radial inflow designs for gases, but there are also outflow designs mainly for steams. So mm, this is based on the application that you have. But for the gases, you will see commonly the radial inflow, and for the steam, you will see radial outflow. But most gas and steam turbines that you're dealing with in a daily actually use, are type of the axial. So if you remember, you had the this shape before for a compressor, and we had this part, and we said this is the compressor, this is the axial compressor. After the compressor, you have the turbine, and this is the axial turbine as well. And you can see that how many stages of blades this compressor has, and how many stages the turbine has. These axial turbines are also multi-stage, but normally the number of the stages inside the axial turbine, I mean the number of rotor stator, is lower than the number of stages in axial compressor, as you can see in here. How many stages of turbines do you see in here? Two or three. But how many stages of compressor blades you're seeing here? Maybe 10, 12. I don't know. Can you say why it is happening here? Why is it like this? No answer. Osman Veysel Özdemir. Energy loss. So if can you explain it for me? Mm, if you can explain, you by the way, if you want, you can join by your microphone and can have a discussion on that. Energy loss. So Mehmet Nurullah and Yunus Mujahid as well. Do you have any idea? I mean, flow turns the turbine and it rotates the compressor. Okay, my question is that um, I'm showing, let's say, in here, I'm showing you an axial gas turbine in here. Okay, this is turbine part. And as Osman said, this turbine is rotating this compressor, right? But if you are looking, if you look at this turbine, you can see that this turbine has a smaller number of stages, like two stages. But the compressor that is actually attached to this turbine has too many numbers of stages. Why is it happening here? Why the number of turbine stages are always smaller than the number of compressor stages? No idea. Osman Veysel says, I don't know. Okay. Nobody knows. Okay. See, you have a jet engine, for example. Inside this jet engine, you have this combination. First, the air comes inside, it hits the compressor blades. These compressor blades are rotating and compress the air. They are compressing the air. And then what is happening? This compressed air goes into the combustion chamber. Then it is mixed up with the fuel. It burns, and you have a very high energy flow. Now this flow goes inside the turbine, and turbine blades, they are there just to extract this very, very high energy from the gases to what? To just rotate the compressor and also to give this gas to the nozzle, and this nozzle uh, shoots the air outside as a jet, and then your airplane flies, right? So, what I meant there, I said that compressor gets the air and it compresses the air. So just imagine how a fluid flows naturally. Naturally, a fluid flows from higher pressure region to lower pressure region, right? So when you have a compressor, you have something that at entry you have low pressure, at the exit you have high pressure. So naturally, air wants to go back outside the compressor, right? From higher pressure region to a lower pressure region. What we should do to not allow the air to come back, because right now air is inside a pressure gradient that we don't want. It's a adverse pressure gradient. So the pressure is increasing. If you remember from your courses in aerodynamics or fluid mechanics, when you have adverse pressure gradient, you have uh, a stall, right? Do you remember? Because air cannot stick to the airfoil, and then the airfoil stalls. So what we can do, just not allowing the air to stall inside the compressor, we have to carefully increase this pressure by means of a number of stages inside. So in each stage, we are carefully increasing the pressure just a little bit, and then in the second stage, just a little bit. We are very careful about the increasing the pressure, because if we just increase the pressure too much, then we get the stall. We get to the stall in the blades. But on the other hand, you have the turbine. The turbine is there just to extract the energy. So do whatever you want to do to the flow. It doesn't want to. It naturally, it inherently, it wants to go from high pressure to low pressure, and turbine is working from high pressure to low pressure. So it means that you can give whatever angle to the flow, and it can also stall. It never mind, because the pressure is normal. You have a you don't have a adverse pressure. You have a favorable pressure gradient. That's why there is no problem with the turbine. So in just one or two stages, you can take all the energy of the fluid and give it to the shaft, and also the uh, to the exhaust as a jet. Is it clear? Because so the answer to this question is that because compressor is working in adverse pressure gradient, but turbine is working in favorable pressure gradient. So we have to be careful about the rise of the pressure inside compressor stages. But on the other hand, there is no need to be careful about that inside a turbine. Is it clear to everyone, or should I explain it more? Okay. And on the right, you're seeing an axial turbine, an axial steam turbine. Uh, And if you're looking at the axial steam turbine and compare it with the axial gas turbine, you are seeing a very large increase in diameter. See, these are small diameter, but the diameter is increasing largely along the axis. Why is it happening? It happens due to the high expansion rate of steam. So a normal gas turbine does not have a high expansion rate, but a steam has a very high expansion rate. That's why you are using very high diameter blades. Okay. Um, these are again some of the basic things that you have to understand. The first thing is that we said that we have an interact between fluid and turbo machine, interact of energy, and this is in one side, and in another side we have interact of angular momentum as well. And this energy is in enthalpy form, this momentum is in torque form. So angular momentum, we are talking when we are talking about the angular momentum, we are talking about something that is rotating. And as you can see, this is the difference between the linear and angular momentum in here. So if you have a machine, uh, if you're talking about linear momentum, it means that some force is actually applied to this machine. But if you're talking about angular momentum, you have a torque applying to the machine. So when we are talking about turbo machine, we are always talking about torque and angular momentum. And this is a reminder to you, there is a relationship between the power of the turbo machine and the torque of the turbo machine. So what is this relationship? It's actually the constant of this relationship is the RPM, or rotational speed of this turbo machine. Your power is actually your torque times your RPM. So this omega is your RPM. In other words, we can say that RPM, or omega here, is the physical parameter which links the energy to the momentum.